I welcome you all in this lecture on simulation of wheeled mobile robots. So, here essentially we will be looking at a brief about the wheeled mobile robots, and then we will be mostly interested in knowing the say kinematics and dynamics of single wheel, two wheel and omnidirectional wheel mobile robot. So, these wheel mobile robots are part of what we call it as mobile robots, and under mobile robots basically there are two types. These types are, so we have the mobile robots, and these mobile robots could be wheeled and legged. So, the beautiful thing about wheeled mobile robots are that one can achieve a greater speed, greater speed as compared to the legged robot, who are usually slow, fine. But the drawback for the wheeled mobile robots are they are not suitable for uneven terrain, whereas legged robot can be used in uneven terrain. So, this is say these are the feature of wheeled and the legged mobile robot. Not useful, uneven terrain they are useful, fine. So, with this small background, let us see the wheeled mobile robots. So, several robots are now designed to have mobility, and of course, they can move on surface, water, as underwater robots or in air. The one which you are seeing these days, that is quadcopters. So, these are there. Now, more recently autonomous robots with legs and or a combination of wheel and legs, that we call it as the hybrid one, have been built for mobility on a surface. The vast majority are wheel mobile robots, are in short they are written as WMRs, as they are more efficient and faster than legged or tracked vehicle, as I explained you over here. These autonomous vehicles are used in industrial environment to move material from one place to another, and they are also used in hazardous environments such as inside the nuclear reactor or of course in the deep sea bed, also used for planetary exploration. Now, analysis of these wheeled mobile robots involves kinematics, dynamics, and these robots moving on a flat surface or in a plane. Of course, there are many more things. For example, we can study the control aspect also, but in this course I will be limiting my discussions to kinematics and dynamics. So, wheel mobile robots are modeled as can be model, that is we can look for the modeling of wheels, and these wheels are modeled as thin disc rolling or sliding on a flat surface. And of course, there has been many authors who have worked a lot in this area, and few of them are Muir and Newman, then Alexander and Maddox, and from India Professor Ghosal has done lot of work in this area, and in fact most part of my lecture here covers from the textbook on robotics written by him. A wheeled mobile robot is a robot capable of locomotion on a surface solely through the wheel assemblies mounted on it and in contact with the surface. Okay. And of course, wheel assembly is a device which provides or allow relative motion between the mount and the surface on which it is intended to have a single point of rolling contact. In practical wheels, due to deformation, there are area contact and we rarely find the point contact between the wheel and surface. There are different types of wheels which are used in wheel mobile robots. These are conventional wheels, omnidirectional wheels and the ball wheels. Let us see one by one. This is an example of the conventional wheel where you can see that here is the axis about which this wheel rotate, and we can put actuators here and that actuator can be mounted on this frame, and the shaft can be engaged to the wheel here. Okay. And of course, from here there can be connection to the robot body. So, these conventional wheels are most commonly used wheels, and these have rotation about axis of the wheel. So, they rotate about the axis which is passing from here, as well as the steering is also possible, that is you can turn about this axis also. Next is the omnidirectional wheels. As you can see in this figure, these wheels are also called Swedish wheels, and in these wheels you can see that there are barrels in the periphery. Okay. And because of these barrels, what happens, these wheels are able to slide in the lateral direction also. Okay. And here is the axis along this one, here axis of the shaft which passes through this hole, and the wheel turns about that axis. So, here barrel can rotate at an angle to the wheel rotation of axis, and here you can see that these barrels are perpendicular, barrel axes are perpendicular to the wheel rotation axis. Okay. And these barrel rotations are usually not actuated, and barrel rotation leads to the sliding of the wheel. So, here we have the 2 degree of freedom in each wheel, and of course, the steering. Then we have the ball or spherical wheels. Here you can see that these there is a frame basically, and this frame is attached to the robot body. It can be bolted from here. Okay. And there is a spherical ball shaped wheel which is here. Okay. So, these are essentially a sphere which can rotate about 2 axes, and complicated drive and rotation measuring arrangement, of course, here all those things have not been shown. Now, let us see the kinematics of a single wheel. Fine. So, if we talk about a single wheel, okay, so say this is the wheel basically, and say this wheel is passing through this curved path, and say this is the point of the contact, and at that the point of contact there is a tangent here at x and y I have drawn here, and say this is the axis of rotation of the wheel. So, this is my x direction and this is my y direction. So, the configuration space of the wheel here consists of specifying x, y and phi. Okay, x, y are the point of contact here, and phi what we call it as the steering angle. Okay. And say wheel are rolling without slip, and that is motion is only along tangent to the path and it is not perpendicular to the path, that is the motion is not there in the lateral direction. Then that is what we call this also as the wheel rolling without slip. Okay. So, if we implement without slip condition here, okay, then we can see that this is the direction for x dot and here is the direction for the y dot. Okay. Then the perpendicular to the wheel here that is the perpendicular to the tangent. If you resolve these velocities, then that should be equal to 0 because there is no slip. Okay. So, this is x dot x component here. So, here you can see that say this is my x and this is phi. Okay. So, this if this is my direction for x dot, so this is going to be x dot sin phi, and likewise we will have the say this is the direction for y dot, this is the y direction. So, our y dot is going to be here. So, here this phi, so this is yes 90 minus phi. So, this is again phi. So, this component is going to be y dot cos phi. So, what we have is x dot sin phi minus y dot cos phi is equal to 0. Okay. So, x dot sin phi minus y dot cos phi is equal to 0. So, this is the condition for the no slip. Okay. So, this is the condition such that your wheel is not moving in this direction. Okay. Wheel is not moving in that direction, that is the velocity perpendicular to the tangent vector is 0. Now, this type of constraint, okay, what we are seeing from here is as x dot sin phi minus y dot cos phi is equal to 0. This type of constraint is what is called a non-holonomic constraint. Okay. This is non-holonomic because this equation cannot be integrated to obtain a function such as f x y phi is equal to 0. That is, here the constraint equation which is in terms of velocity and which cannot be integrated in order to get a constraint equation in terms of displacement, that type of constraint is called the non-holonomic constraint. Okay. So, the constraint q dot is equal to x dot y dot phi dot transpose and not in terms of this one. So, this is the non-holonomic constraint. Now, we can give the justification for the non-holonomic nature of this expression. Okay. So, we can assume that, let us see that this expression can be integrated. Now, if I am able to integrate this expression and get the expression integrated expression in terms of displacement. So, this implies that existence of some f x y phi is equal to 0, that is the 3 unknown with one constant equation. So, here there are 3 unknowns, that is x y phi, okay, and f x y phi with 3 unknowns here. Okay, we will be having a constant equation here. So, what does this means? This means that if I know any of the 2 parameters, say x y, I can find out phi. Okay. So, by choosing any of 2 x y phi, we can determine the third component. Now, suppose if I take x y is equal to 0, we get a phi value which is a constant and of course, which is determined from the constraint relation. Thus, no other values of phi is possible, and of course this is not true, because as we have seen in this example, the disk is steerable, okay, that is phi can change, it cannot remain constant. So our assumption that this expression can be integrated in order to get a function in terms of x, y and phi, that is totally wrong. Okay. So, it implies that this expression is a non-holonomic expression, that is, by integrating this you cannot get a displacement relationship. Okay. So, this is not integrable. Now, the kinematics of a single wheel can be given by this expression. It is a very simple expression. Of course, if we know that how the wheel is moving, that is, if we know the wheel velocity, then we can find out this kinematic equation. So, suppose we have the tangential velocity of the wheel, this is v, and say this is my x direction and this is my y direction, okay, and say this angle is phi, then we know that what is my x dot and y dot. So, x dot will be v cos phi and y dot will be v sin phi, okay, and of course the phi dot will be omega, and I can write this expression in the matrix form like this: x dot is v cos phi, y dot is v sin phi and phi dot is equal to omega. Okay. Here v and omega are the forward speed and the steering rate. Okay. So, here this omega is the steering rate. Now, let us see the two-wheeled robot, which is very similar to that of the bicycle model. Okay. So, in this one, say this is the two-wheel robot and say this is the rear wheel and this one is the front wheel. Now, in this case there are 4 generalized coordinates which we can observe. These coordinates are the xy point of contact of the rear wheel here, okay. We have the psi, that is orientation of body and rear wheel with x axis. This is orientation of body as well as rear wheel with x axis, and there is another generalized coordinate phi, which is the steering angle of the front wheel with respect to the body. Okay. So, this way we can define the 4 generalized coordinates here, and we have the x and y, say this is my 0th frame, or what you can say that this is the absolute frame. Okay. So, here there are 2 rolling constraints in each wheel. In this case we can work it out. The first one is this one, x dot sin psi minus y dot cos psi is equal to 0. This is basically the no slip condition here, okay, no slip condition here, and the second one here is the no slip condition here. Okay. So, and here you can see that this is because of the translational velocity and this term is because of the angular velocity that is there. Okay. And we can so these are the constraint in each wheel, and the kinematic equation for this can be written like this. Basically, here Vf is the forward that is the velocity of the front wheel. So, I can find out its component in the direction of the wheel axis. So, this will be Vf cos phi, and of course, this Vs cos phi I can resolve in x direction. So, that will be Vf cos phi and cos psi. So, here we have got x dot as Vf cos phi cos psi. Similarly, the y component I can get, that is Vf cos psi phi and its sine component. So, Vf cos psi cos phi and its sine component here, okay. And the psi dot I can get, basically this Vf will also be equal to L psi dot sine phi, okay. So, from here I can get this value of psi dot, and of course phi dot will be given by omega, okay. Line perpendicular to the front and rear wheel velocity vector meet here at say the C, which is the instantaneous center of rotation. So, here we have seen the constant equation for the wheel as well as we have seen the kinematic equation. Likewise, similar to the two wheel, we can work for the three wheel also. Here you can see that there are two rear wheels, okay, and you have a front wheel, fine, and say C is the instantaneous center of rotation, and of course everything expressed with respect to a zeroth frame, that is x and y frame. Now, here you can see, as we have seen in the previous case, this the front wheel is steerable here, it is steered, and the speed of the rear wheels are different, of course, when they are making a turn, okay. And we can represent the wheel speed for each wheel by say r theta I dot, where of course I is equal to 1, 2 to 3 for different wheels, and r of course the radius of the ith wheel. Now, here we can see that one rear wheel is driven and the speed of the second rear wheel must adjust so that there is a single instantaneous center of rotation, okay. And if the second rear wheel can be free, that is what implies from the first statement is that the second rear wheel can be free or a differential has to be used. Of course, the kinematics I am not going to deal here, it is very similar to what we have seen previously, the bicycle model, okay. And this C here determines relation between the R, that is the distance of the robo axis from the instantaneous center, theta I, that is the individual wheel rotations, radius of the wheel, L, that is the distance between the front and the rear wheel, okay. And this is the vehicle turning psi and the steering angle, okay. And if there is no single C, then of course as we all know from our basic kinematics understanding that we are going to have the slip. Next we will see the omnidirectional wheel, okay. In omnidirectional wheel there are actually 6 equally spaced free barrels on the periphery, as I have shown these barrels in initial slides. Now, each barrel can rotate about its axis, we have also seen, and this is basically responsible for giving the lateral motion to the wheel. Usually the 2 rows of barrels are used, so that one barrel is always in contact with the ground and the distance of point of contact from the vehicle center changes. Let rotation speed is represented by say theta dot and the sliding speed is represented by say sigma. So, if we want to look at the kinematics of the wheel mobile robots with 3 omni wheels, then here you can see that say this is our first wheel, second wheel, third wheel, okay, and these wheels are placed at 120 degree each, fine. So, here the tangential velocities are V1, V2, V3, and of course, these are the slip velocities sigma 1, sigma 2 and sigma 3 are here, okay. So, no steering wheel rotational speed theta dot I, where I goes from 1 to 3, and we can find out the kinematics for no slip condition, and we can find out this theta 1 derivative, theta 2 derivative, theta 3 derivative, okay, as a these are a certain matrix into the say Cartesian velocity vector. Okay. So, this is somewhat very similar to what we have seen in robotics, industrial robots, okay, where we had a matrix multiplied by joint velocities and we were getting the Cartesian velocities. Here we have a matrix multiplied by the Cartesian velocities in order to get the individual wheel rotations. Okay. So, this can be worked out by going through the simple working out the simple kinematic equation for this one. Translational and rotational dynamics of a wheel, if I try to understand, then you can see that say there is a wheel here, there is a rigid ground, we have the deformable wheel, this is the forward direction, say velocity is x derivative, okay, this is the rotation, a torque tau on acting here, and there is a rigid ground, normal reaction is n and the traction force is Ft. So, the translational dynamics here consist of Ft is equal to say mass of the wheel into acceleration, okay, and the rotational dynamics will be equal to, that is the is given by tau torque, and this torque will be basically what this torque we can find out by writing torque minus this traction torque, that is Ftr is equal to the j of wheel into the acceleration of the wheel, angular acceleration of the wheel. Okay. So, here Ft is tractive force at the wheel ground interface and tau is the torque applied as the wheel axis. So, these two expression gives the translational and rotational dynamics of the a wheel. And the last we can similarly work out the equation of motion for the omnidirectional mobile robot, okay, and this equation of motion one can obtain by using Lagrange equations. Okay. So, we can evaluate the kinetic energy, we can evaluate the potential energy, we can find out the Lagrange, and then by substituting in Lagrange equation we can get the expression. The expression looks like this one. So, we have the kinetic energy of the platform is there and the kinetic energy of wheels are here. We assume that there is no potential energy as the motion is on the flat plate. Okay. So, here let us try to understand this expression which is of this form. So, here are the MP or the mass of the platform. So, you have the mass of the platform into acceleration of the platform in the x direction, likewise mass of the platform and acceleration of the platform in y direction, and here this is the polar moment of inertia of the platform and the angular acceleration of the platform. Okay. So, plus you have a matrix here, and of course, here we have the velocity vectors, and there is also the vector psi dot, and this is equal to r into this rotation matrix which we have seen previously, that transpose into here the traction forces. Okay. These traction forces we can find out from this equation, okay, and this equation is nothing but expression for the individual wheels. So, here we have the I1, I2, I3 and the wheel accelerations plus R into Ft1, Ft2, Ft3, that is these are the traction torque, and these equal to the torque of the individual motors, okay, applied on the individual wheels. Okay. So, now we can use these expressions and give the numerical values in order to do the simulations. Okay. So, I will stop here. You can try simulating these expressions, and for further details please refer to Asitawa Ghosal Robotics Fundamental Concept and Analysis, where you can find out many simulation results for the given set of parameters. Thank you.